Section. Introduction. We're here to talk about large language models, LLMs, which have become a key part of the rapid growth of cloud services. These models are essential for advancing AI applications, but they come with their own set of challenges due to their huge computational and data needs. Typically, these services use multiple GPU cards working together to handle LLM tasks. However, the dynamic nature of LLMs can lead to complex computational problems. At the core of LLM services is the process of autoregressive text generation. This is where the model generates one word, or token, at a time, and each new word is added to the existing text. This process continues until the final word is generated. The memory and computational resources needed for LLM services can change throughout the service, and we can't predict the lifetime or the length of the sequence in advance. This makes it hard to plan resource allocation ahead of time, which can be a big challenge when designing efficient LLM service systems on the cloud. In tasks that involve a lot of context, the key value, KV-cache, can exceed GPU memory limits within a computing instance. This means we need to reallocate resources right away, which can involve either moving the task to a more capable instance or assigning extra GPS to handle potential memory overloads. However, the latter can lead to inefficiencies and wasted resources, especially in tasks with normal length contexts. Previous work, like DistAttention, has tried to solve these problems by allowing data to be swapped between GPU and CPU memory. But this approach has its limitations. For one, DistAttention's memory swapping is limited to the GPU and CPU memory within a single node, which restricts its ability to handle very long context lengths. Also, while its paging strategy is designed to minimize memory fragmentation, it swaps entire KV caches on a request-level basis, which means it misses the opportunity for more adaptive, granular scheduling in a distributed cloud environment. Finally, the interruption of computation for swapped-out requests can cause performance issues for the running task, which can risk not meeting the strict service-level agreements, SLAs, that are crucial for cloud services. To address these challenges, we propose DistAttention, a new attention algorithm. DistAttention divides the KV cache into R blocks, uniform subblocks that make it easier to manage the distributed computation and memory of attention modules for LLM service with long context length. Unlike traditional methods that mainly use GPU or CPU memory within a single node, DistAttention allows for optimization opportunities of all accessible GPU or CPU memory resources across the data center, especially those that are currently underused. This not only supports much longer context lengths but also avoids the performance issues typically associated with data swapping or live migration processes. In this paper, we developed DistKV-LLM, a distributed LLM service engine that works seamlessly with DistAttention. DistKV-LLM is great at managing KV cache, efficiently coordinating memory usage among distributed GPUs and CPUs across the data center. When an LLM service instance runs out of memory due to KV cache expansion, DistKV-LLM proactively looks for extra memory from less burdened instances. Moreover, DistKV-LLM introduces a complex protocol that allows for efficient, scalable, and coherent interactions among many LLM service instances running in the cloud. This protocol is designed to manage and balance the large amount of memory resources effectively. Additionally, DistKV-LLM prioritizes data locality and communication optimization, which are key for addressing performance challenges associated with the distributed storage of the KV cache. In summary, our work aims to fully utilize all the available GPU resources across the data center, ensuring a smooth and efficient cloud service for LLMs, especially when handling long context tasks. The combination of DistAttention and DistKV-LLM offers a solution to the resource allocation and optimization challenges faced by LLM services in distributed environments. This approach enables efficient resource management, allowing LLM services to handle a wide range of context generation tasks effectively. We tested DistKV-LLM in a cloud setup equipped with 32 NVIDIA A100 GPUs, testing various distributed system configurations ranging from 2 to 32 instances. Our assessment included 18 benchmark datasets with context lengths extending up to 1,900 K. Our system demonstrated performance improvements of 1.03 to 2.4 times over state-of-the-art work and a capability of supporting 2 to 19 times longer context lengths. This paper makes the following contributions. 1. We present DistAttention, an innovative attention algorithm designed to significantly advance distributed computing for large language models, LLMs, on the cloud. This algorithm is particularly adept at handling dynamic and diverse context generation tasks. Crucially, DistAttention unlocks the potential to fully utilize all available GPU and CPU memory resources across the data center. 2. We introduce DistKV-LLM, a distributed LLM service engine, which excels in providing efficient, scalable, and coherent management of distributed KV-caches, harnessing the vast memory resources within GPU clusters on cloud infrastructure. DistKV-LLM also effectively optimizes memory locality and communication overhead, ensuring a smooth and efficient cloud service for LLMs. 3. We demonstrate the feasibility and efficiency of the combination of DistAttention and DistKV-LLM in a cloud environment with 32 NVIDIA A100 GPS and 18 datasets with up to 1900K context length. Our system outperforms state-of-the-art work, delivering support for context lengths that are 2 to 19 times longer and achieving 1.4 to 5.3 times higher throughput in tasks with standard length contexts. In the following sections of this paper, we'll provide more background information, outline the key challenges of serving LLMs on the cloud and our main idea, delve into the details of our design, describe our implementation details, present our evaluation results, provide an overview of related works, and conclude this work. Section Summary. Large language models, LLMs, are crucial for advancing AI applications, but their dynamic nature poses challenges in resource allocation for LLM cloud services. To address this, we propose DistAttention, an attention algorithm that partitions the key value, KV-cache, into sub-blocks, enabling distributed computation and memory management across the data center. We also introduce DistKV-LLM, a distributed LLM service engine that efficiently coordinates memory usage among distributed GPUs and CPUs, effectively managing the KV-cache and optimizing data locality. Our evaluation shows that our approach outperforms state-of-the-art work, supporting context lengths that are 2 to 19 times longer and achieving higher throughput in tasks with standard length contexts. Section. Background. We're going to delve into the world of large language models, LLMs, which have been a game changer in the field of natural language processing. These models have a wide range of applications, from generating simple text to solving complex problems and even powering conversational AI. LLMs are built on the foundation of the transformer model, a sophisticated architecture that allows them to understand and generate human-like text. Take GPT-3, for instance, one of the largest models out there. It's made up of numerous transformer blocks, or layers, and has a whopping 175 billion parameters. This allows it to capture intricate language patterns. Each transformer block is made up of several key components. First, there's the QKV linear layer, which is essentially a fully connected neural network. It takes the input and projects it into 3 different spaces: queries, Q, keys, K, and values, V. Next, we have the multi-head self-attention mechanism, the heart of the transformer block. This mechanism allows the model to assign different levels of importance to different parts of the input sequence. It does this by transforming the input multiple times to form different heads, which allows the model to focus on different representation subspaces at different positions. Finally, there's the feed-forward neural network, which comes after the self-attention module. This is a 2-layer neural network with a ReLU activation function in between. The network is the same for different positions, but the parameters vary from layer to layer. When it comes to using LLMs, the process starts with the model receiving a prompt or input text from the user. The model then processes this input to understand the context and the nature of the task required, such as answering a question or writing a poem. Given an initial text made up of tokens, the model predicts the next token. It does this by calculating the probability distribution, which represents the likelihood of each possible token being the next one. This calculation involves parameters learned from the final layer of the transformer model and the hidden state vector associated with the last word. In the auto-regressive phase, the model generates one word at a time, with each new word being based on the sequence of words generated so far. This phase is iterative and continues until the model produces a complete and coherent response or reaches a predefined limit, like a word count. LLMs require a lot of computational power and memory resources. To manage this, several parallelism strategies are used to distribute the workload and speed up processing. Data parallelism is used to handle the large volume of requests in cloud environments. The model is replicated across the data center, with each copy operating independently and processing different batches of requests concurrently. Batching strategies are also used to improve throughput by processing a greater number of requests simultaneously. Model parallelism is another technique used when the model can't fit entirely within the memory of a single GPU. The model is split across multiple devices or nodes. This can be done in two main ways: pipeline parallelism, where the layers of a model are split across multiple devices, and tensor parallelism, where the model's layers are split across multiple GPUs. This is particularly important for LLMs when individual layers of the model are too large for a single GPU. Section Summary. Large language models, LLMs, like GPT-3 have a sophisticated architecture based on the transformer model, consisting of transformer blocks with multiple components such as QKV linear layers, multi-head self-attention mechanism, and feed-forward neural networks. During inference, LLMs go through a prefill phase where they receive a prompt and predict the next token based on the input. In the autoregressive generation phase, the model generates words one at a time based on the sequence generated so far. To handle the computational demands of LLMs, parallelism strategies like data parallelism and model parallelism are employed, allowing for distributed processing and improved throughput. Section. Motivation and main idea. We've noticed a significant increase in the development of long context language learning models, LLMs, with the context window growing from 2K to a whopping 256K in just a year. This trend shows no signs of slowing down, as applications of LLMs now require support for even longer contexts. However, this growth in context length presents considerable challenges for LLM systems, especially due to the increasing computational and memory needs for key-value (KV) caches. This trend is evident in the Llama 2-13b model, where the KV cache size increases in direct proportion to the growing context length. Current graphics processing units, GPUs, with memory capacities of several dozen gigabytes, are being stretched to their limits, requiring more memory space to accommodate the growing size of KV caches. In this study, we aim to make the most of the vast memory capacities of GPUs and central processing units, CPUs, available in data centers. Our goal is to create an efficient memory pool specifically designed for LLM services that can handle extremely long context lengths. However, developing such a system is not straightforward. We've identified two main challenges when it comes to serving large language models with extended contexts on cloud platforms. The first challenge is the significant differences in memory demands, which hinder efficient model parallelism. Unlike the continuously expanding KV cache during the auto-generation process, the memory requirements for the remaining activation tensors stay the same. This difference between the attention layer and other layers presents a significant challenge for efficiently implementing model parallelism. To accommodate the extensive KV cache necessary for long context tasks, more GPUs are needed. However, tensor dimensions in other layers do not scale with context length. As a result, traditional model parallelism leads to more fine-grained subdivisions of these layers when distributed across more GPUs, resulting in less efficient resource utilization. Some previous studies have suggested dividing KV caches into smaller blocks for more fine-grained memory management, aiming to prevent memory fragmentation. While these approaches have separated the KV cache of attention layers from the transformer block, they still rely on gathering and positioning all blocks within the local GPU memory to carry out the attention module's computation. In contrast, our design goal focuses on storing KV caches and executing attention modules in a distributed manner, essential for effectively utilizing the abundant resources available in cloud environments. The second challenge is the dynamic nature of KV cache size, which leads to inefficient resource management in the cloud environment. The auto-regressive design's inherent nature determines that the ultimate sequence length remains unknown until the generation process reaches its conclusion, typically marked by an ending character. As a result, memory requirements are entirely dynamic and unpredictable, fluctuating significantly in scale. The demands can range from a few gigabytes to several hundred gigabytes, which is continuing to escalate even further. This variability prevents any form of resource planning in advance. Resources must be allocated or released dynamically, reacting to the real-time demands of the auto-regressive process. If the memory required for a context exceeds the capacity of an instance's GPUs, the entire task must be transferred to a larger instance with more GPUs, a process known as live migration. Live migration is resource-intensive and, as our experiments show, can be 25 times more costly than a standard inference. An alternative, allocating more GPS to a computing instance from the outset, can lead to resource wastage for tasks involving shorter contexts, thereby compounding the challenge of efficient resource allocation. DistAttention addresses the management of KV-caches by employing fine-grained subblocks, analogous to pages in operating systems. However, this approach is confined to utilizing only CPU memory for swapping, a method that proves inefficient on the cloud. The limitation imposed by the finite CPU memory not only restricts the maximum context length supportable by LLM services but also fails to capitalize on the expansive memory resources distributed across the cloud. In contrast, our objective is to harness the extensive memory capabilities of both GPUs and CPUs within data centers. We aim to establish an efficient memory pool, meticulously crafted for LLM services, to support the processing of exceptionally long context lengths effectively. Motivated by these challenges, we present a set of key techniques specifically designed to address them. Together, they form a comprehensive and systematic approach, ensuring efficient LLM serving capable of handling extended context lengths. To address the first challenge, we introduce a new attention algorithm named DistAttention. This algorithm breaks down the traditional attention computation into smaller, more manageable units known as macro-attentions, MAS, and their corresponding KV-caches, R blocks. This innovative method facilitates the decoupling of KV-caches computation from the standard transformer block, thereby enabling independent model parallelism strategies and memory management for attention layers versus other layers within the transformer block. For non-attention layers, we apply established model parallelism strategies. In contrast, the attention layers are managed adaptively, dynamically allocating memory and computational resources across the data center in response to the fluctuations of the KV-cache. To overcome the second challenge, we present DistKV-LLM, a distributed LLM service engine seamlessly integrated with DistAttention. The DistKV-LLM is designed to provide an efficient KV-cache management service, coordinating memory usage across GPUs and CPUs throughout the data center. When an LLM service instance encounters a memory shortfall due to an increase in the KV-cache, DistKV-LLM proactively identifies and borrows available memory spaces from other instances that have excess capacity. This automated mechanism is realized by collaborative operations of two major components, the R manger and the G manager. The R manger virtualizes all the GPU and CPU memories within each LLM service instance, handling memory operation requests from both local and remote instances. Simultaneously, the G manager operates as a global coordinator, maintaining a protocol that ensures effective, scalable, and coherent resource management among distributed R managers. Moreover, DistKV-LLM proposes a new algorithm, called DGFM, that effectively addresses the issue of memory fragmentation in the distributed KV-cache environment of the data center. This joint effort ensures continuous and efficient memory utilization, thereby enhancing the overall performance and reliability of the LLM service. In summary, our integrated approach with DistKV-LLM and DistAttention presents a robust and scalable solution to the unique challenges posed by long-context LLM serving on the cloud. By addressing key issues related to memory management and computation scheduling, we ensure that LLM services can operate efficiently and adaptively in the cloud. This innovative framework not only optimizes resource utilization but also paves the way for future advancements in the field of large-scale language model deployment. We present details of our design in the following sections. Section Summary. The motivation behind this work is to address the challenges faced by large language models, LLMs, when serving long contexts on cloud platforms. The main idea is to introduce a new attention algorithm called DistAttention, which breaks down attention computation into smaller units and enables independent model parallelism and memory management for attention layers. Additionally, a distributed LLM service engine called DistKV-LLM is proposed to efficiently manage the KV-cache memory across GPUs and CPUs in the data center, ensuring continuous and efficient memory utilization. Section. Overview. Let's dive into the details of our innovative approach to managing distributed key-value, KV, cache. We've developed a unique attention algorithm called DistAttention, which is designed to simplify the management and computation of distributed KV cache. This algorithm is the foundation of our large language model, LLM, serving engine, DistKV-LLM, which is specifically designed to manage KV caches in distributed GPU memory on a large scale. Our approach consists of several key components. First, we introduce the R Manager, a software layer that acts as a virtual memory manager for each LLM service instance. It provides an abstraction layer for basic memory blocks, which we call R blocks, to improve memory management efficiency. Next, we introduce the G Manager, a global management system that ensures effective, secure, and coherent management of R blocks across distributed GPUs in a data center. We also propose an innovative algorithm designed to aggregate fragmented memory blocks, which significantly improves data locality within the distributed KVCache system. Lastly, we propose a series of optimization strategies designed to reduce the communication overhead associated with the distributed storage of the KVCache. These strategies work by effectively overlapping computation and communication tasks. Now, let's delve into the specifics of DistAttention. This algorithm breaks down the KVCache into smaller, more manageable subblocks, making distributed memory management across the data center easier. The algorithm divides DistAttention into multiple microattentions, MOS, each of which handles a subsequence of KVCache tokens. The unique aspect of this design is its ability to compute the attention result by performing MOS separately. Once all MOS have completed computations on their respective subblocks of tokens, the final attention results are obtained through an aggregation process. This process involves scaling and reducing the outputs of each MA. This approach not only consolidates the computations performed by individual MOS but also efficiently synthesizes them into a coherent final output. With the implementation of DistAttention, the key value, KV, caches of LLMs are segmented into smaller units, known as R blocks. Each R block contains a set of vectors corresponding to a fixed number of key value tokens, along with essential metadata. This metadata provides critical information about the subblock, such as the R block ID and instance ID, the device ID, and physical ID. Each LLM service instance is equipped with a dedicated R block manager, referred to as the R Manager. The R Manager is responsible for overseeing all the R blocks located in local devices. It effectively virtualizes the global memory space of GPUs by dividing it into fixed-sized physical R blocks. The G Manager, another key component of our system, functions as a centralized manager, maintaining the global memory information across all instances. Each instance periodically sends heartbeat signals to the G Manager, conveying updates about the remaining available memory space. Using this data, the G Manager constructs a detailed table known as the global debt ledger. Whenever an instance runs short of its memory space for R blocks, the corresponding R Manager seeks to borrow GPU or CPU memory spaces from neighboring instances. The G Manager and the R Managers work together to ensure efficient and effective memory space allocation and management across the data center. The global debt ledger, managed by the G Manager, is a crucial table that chronicles the available memory and inter-instance debts across the network. In scenarios where multiple debtor instances concurrently send requests to a R Manager, the system must navigate these competing demands efficiently. The global debt ledger plays an important role here, enabling the G Manager to evenly distribute requests among instances, thereby preventing an overload on any single instance. We employ a loose coherence policy between the G Manager and the R Managers. Under this approach, the G Manager is not required to meticulously track every memory allocation or release action across all instances. Instead, it gathers this information through regular heartbeats that are automatically sent by the R Managers. To meet varying throughput demands, the G Manager is designed to enhance scalability through the deployment of multiple processes that concurrently handle querying requests. This approach ensures that the G Manager operates within its optimal capacity, maintaining system efficiency and responsiveness while scaling to accommodate the dynamic needs of the network. Section Summary. The paper introduces DistAttention, an attention algorithm designed for distributed memory management in KV caches. It disaggregates the cache into smaller subblocks called microattentions, MOS, which compute attention results separately and then aggregate them. The paper also presents the R Manager, a software layer that virtualizes GPU and CPU memories, and the G Manager, a global management system that facilitates memory borrowing between instances for efficient memory allocation and management. Section: Fragmented Memory Management. We're dealing with a complex issue here: managing fragmented memory in a dynamic system. In this system, each unit both lends and borrows memory space as needed. For instance, units dealing with long-term requests may need to borrow space from others, while those with short-term requests can lend their freed-up space. This constant borrowing and lending can lead to a problem. Data locality gets worse. This means that units often have to access data stored far away, which slows down the system and reduces its efficiency. To tackle this, we've come up with a solution: a debt graph-based fragmented memory management algorithm, or DGFM for short. This algorithm works by strategically recalling memory spaces that have been lent out and swapping them for local data storage. The challenge here is that there are many units running at the same time, often with complex borrowing and lending relationships. To manage this, we think of the problem as looking for circles within a directed graph. We create a graph that represents these relationships, with each node representing a unit and each directed edge representing a debt from one unit to another. Our algorithm then works in cycles. In each cycle, it picks a node at random and looks for a directed circle. If it finds one, it means that the units involved can settle their debts by recalling and swapping their memory blocks. This improves the system's efficiency and memory use. We also have to deal with another issue: the communication overhead of transferring memory blocks back and forth in a distributed KVCache storage. During the execution of long context tasks, both the prefill and auto-regression phases can generate a lot of KVCache, which means borrowing remote spaces. We've made specific optimizations for both scenarios. During the prefill phase, we can predict the memory needs of the KVCache based on the length of the prompt. This allows us to plan the allocation of memory blocks in advance. When executing the attention layers of the transformer block, we overlap the computation of attention with the transfer of remote memory blocks. In the auto-regression phase, memory blocks are allocated dynamically. If we were to bring all memory blocks back for local computation, it would cause too much network traffic. Also, because the attention module's computation is a memory-intensive task, localizing all computations can severely degrade system performance. Our solution, DistAttention, allows us to send query vectors to the unit containing the remote memory blocks, do the computations there, and then send the results back. This reduces data transfer volume by a factor equal to the number of tokens in the KVCache. However, this method could compete for computational resources with the host unit of the remote memory blocks. To prevent this, we set a threshold within each unit, which decides the borrowing of computational resources based on local guidelines. This ensures a balanced and wise use of the system's computational resources. As for the implementation details, DistAttention consists of two types of operators: DistAtten and scale-reduce, developed with about 5,000 lines of C++ CUDA code. The DistAtten operator is designed for distributed attention computation, with the results consolidated by the scale-reduce operator to yield the final outcome. To manage a wide range of input context lengths, DistAtten includes an adaptive kernel selection process based on the dimensions of the inputs. We've developed and optimized 3 distinct kernel templates for different context lengths. We've also implemented a heuristic approach to fine-tune CUDA kernels for specific tensor shapes. On the other hand, DistKV-LLM uses the Ray framework to establish a distributed KVCache management and scheduling system, developed with around 12,000 lines of Python code. For effective implementation of requests and network data movements, we customize the package encodings and transfer data packages with socket, instead of using an RPC-based framework. To maximize the benefits of high bandwidth, NCCL is used for cross-instance GPU tensor communication, ensuring efficient data exchange among distributed units. Section Summary. The fragmented memory management challenge arises due to the dynamic nature of variable context length and batching, resulting in instances borrowing and lending memory space. This leads to a deterioration of data locality and performance penalties. To address this, the proposed DGFM algorithm strategically recalls memory spaces that have been lent out and swaps them for local data storage, improving system efficiency. Additionally, communication optimization is achieved by predicting memory demands, overlapping computation with remote R-block transfer, and redirecting query vectors to instances containing remote R-blocks, reducing data transfer volume. The implementation details include DistAttention and scale-reduce operators for distributed attention computation and a customized package encoding and transfer system for efficient data exchange. Section: Evaluation. In this section, we'll discuss the results of our evaluation. We tested our system, DistKV-LLM, on a cluster made up of 4 nodes and 32 GPS. Each node was equipped with 8 NVIDIA A100 GPUs, each with 80 GB of memory. Our system is designed to support a variety of popular language learning models, LLMs, such as GPT, Llama, Bloom, and others. For our evaluation, we chose to use Llama 2 as a representative model because most LLMs share a similar transformer block structure. The Llama 2 model comes in three sizes: 7B, 13B, and 70B. The 7B and 13B models use a multi-head attention (MHA) architecture, while the 70B model uses a grouped query attention (GQA) architecture. We compared our system to VLLM, a leading LLM serving engine, and also to previous LLM service systems that use tensor parallelism. To test the effectiveness of pipeline parallelism with contiguous batching, we implemented a similar design in ALPA in the VLLM framework. We tested our system using 18 different datasets, each containing 1,000 text generation tasks based on real-world scenarios. These datasets were divided into three categories based on the length of the context. The context lengths in these datasets ranged from 1 to 1,900K, with the proportion of long context tasks ranging from 1% to 30%. We compared the performance of DistKV-LLM and the baseline on different context lengths using three models with different context ranges. For the Llama 2 to 7B model, we tested tasks with context lengths of 1 to 200K on 2 GPUs, 1-1200K on 16 GPUs, and 1-1900K on 32 GPS. For the Llama 2 to 13B model, we tested context lengths of 1 to 280K on 4 GPUs, and 1 to 480K on 8 GPS. For the Llama 2 to 70B model, we tested context lengths of 1 to 450K on 8 GPS. Our results showed that DistKV-LLM not only achieved a throughput comparable to VLLM v1 but also supported significantly longer context lengths, approximately 2 to 19 times longer. This improvement is due to DistKV-LLM's ability to efficiently manage memory usage across all instances, while VLLM v1 is limited to the instance's private memory. When compared to VLLM v2, which was pre-assigned with more GPS to support comparable context lengths, DistKV-LLM maintained similar extended context lengths but achieved significantly higher throughput. This is because DistKV-LLM can maintain an efficient model parallelism strategy while VLLM v2 partitions the model into smaller segments across more GPUs, resulting in lower hardware efficiency. We also evaluated the end-to-end performance of DistKV-LLM using the corresponding context range datasets. When the curve rises sharply, it indicates that the throughput has reached the system's limit, requests begin to queue up, and latency increases rapidly. In the dataset with 1% long requests, DistKV-LLM achieves an improvement of approximately 1.4x to 2.4x over the baseline. This is because splitting the model into smaller fragments leads to lower GPU utilization, which considerably reduces the efficiency of linear computations. In the dataset with 10% long requests, DistKV-LLM achieves a performance improvement of approximately 1.1x to 1.4x compared to the baseline. In a dataset where long requests comprise 30% of the data, DistKV-LLM realizes a performance gain of about 1.03x to 1.3x over the baseline. As the proportion of long requests in the dataset increases, the performance gain offered by DistKV-LLM diminishes. This is because when the model processes requests with long context, there is a lower ratio of linear computations to attention computations. The performance gain that DistKV-LLM has in the linear component becomes a smaller fraction of the overall computational workload, and the attention component's performance does not show a significant advantage over the baseline. Section Summary. In the evaluation, the authors deployed DistKV-LLM on a cluster with 4 nodes and 32 GPUs, and tested it with popular LLM models such as GPT, Llama, and Bloom. They compared DistKV-LLM with the state-of-the-art LLM serving engine, VLLM, and demonstrated that DistKV-LLM achieved comparable throughput while supporting substantially longer context lengths. They also evaluated the end-to-end performance of DistKV-LLM and showed that it outperformed the baseline in datasets with different proportions of long requests, with the performance gain diminishing as the proportion of long requests increased. Section. Live migration. Let's discuss the concept of live migration. This is a method that allows us to transfer to a more powerful instance with more GPUs when needed. We conducted an experiment comparing DistKV-LLM and live migration using the Llama 2 to 7B model. Initially, we used an A100 GPU, which can handle requests up to a length of 108,000. If the context length goes beyond this, we need to use an additional A100 GPU. The results showed that the time taken due to live migration was 45 times more than the communication time in DistKV-LLM. When the context length was 105,000 prompt and 5,000 output, it triggered a live migration. This significantly increased the latency of VLLM, while DistKV-LLM only experienced a minor disturbance. When generating tokens of lengths 5,000, 10,000, 20,000, and 30,000, DistKV-LLM was 3.5, 2.2, 1.6, and 1.4 times faster than VLLM, respectively. This is because migrating the entire service results in a lot of overhead, which includes downloading the model remotely and loading the model into the inference engine. On the other hand, DistKV-LLM only needs to establish a connection with the expanded devices without the need for downloading and loading the model. Next, let's talk about optimizing memory allocation. The dynamic nature of variable context length and batching can lead to the deterioration of data locality. The DGFM algorithm aims to optimize memory allocation by recalling lent memory spaces. We conducted an experiment using DistKV-LLM with 4 Llama 2 to 13 BTP2 instances, capable of handling request lengths ranging from 1 to 480,000. We compared the performance of the service with and without DGFM. Initially, the performance of services with and without DGFM was similar. However, over time, the issue of data locality began to emerge. Services with DGFM maintained a higher overall throughput by periodically clearing the det circle and optimizing the overall data locality in the distributed environments. In contrast, services without DGFM experienced a severe problem with data locality deterioration, resulting in a continuous downward trend in overall throughput. Now, let's move on to the ablation study. DistAttention introduces the capability for distributed storage and computation of attention across instances, which also incurs certain overheads. These are primarily due to the transmission costs of the query, key, and value tensors for individual tokens, as well as some other overheads such as tensor slicing and concatenating. We conducted a breakdown analysis of the runtime of DistAttention and compared it with the attention that is divided into 8 parts by tensor parallelism. The additional overhead introduces a 5% to 10% increase in latency. This extra latency is almost constant, which means that as the context length increases, the proportion of this overhead becomes increasingly smaller. We also compared 2 strategies to compute the remotely allocated R blocks. 1. Local compute. Bring back the KVCache from the remote instance via high-speed interconnect network to perform the full attention computation locally. 2. Remote compute. Transmit the query vector to the remote instance, where the R blocks locate, to carry out distributed attention computations, enabled by DistAttention, and then retrieve the result vector back. The latency of local compute is significantly higher than that of remote compute, which is attributed to the fact that local compute requires transferring a large volume of remote KVCache back to the local instance through the network, constrained by network bandwidth, substantially increasing the overall latency. In the section on related works, we discuss existing LLM service systems. Many LLM serving systems have been proposed recently. Orca has introduced an iteration-level scheduling strategy which greatly enhances the computation and memory utilization in batching inference. VLLM has developed a paged KV, key value, cache and paged attention mechanism to address the issue of memory wastage resulting from fragmentation and redundant replication. DeepSpeed FastGen has proposed a novel prompt and generation composition strategy called Dynamic Split Fuse, which is designed to further enhance continuous batching and system throughput. AlpaServe explores the opportunity of statistical multiplexing by model parallelism in the scenario of bursty request rate. Faster Transformer and DeepSpeed Inference have pioneered an extensive kernel-level performance optimizations specifically for transformer models. Tensor RT-LLM and LM Deploy, building upon Faster Transformer, have adapted features like contiguous batching and paged attention. Despite these novel systems solve many problems and achieve outstanding results, the dynamic problem along with the need to support exceptionally long context lengths still remains an unresolved challenge. We also compared ring attention to DistAttention. Ring attention was introduced as a method to distribute long sequences across multiple devices, with the intent of fully overlapping the communication of key-value (KV) blocks with the computation of blockwise attention. This approach is highly efficient for training with long sequences and for the prefill phase during inference. However, during the decoding phase and inference, the transfer of KV blocks between devices cannot be concealed by computation, leading to substantial overhead. Finally, we discussed solutions for long context serving. Another category of methods to address the challenge of managing oversized key-value (KV) cache for long context inference involves sparse KV caches, such as sliding window attention. This technique only requires maintaining a KV cache the size of the window. Both H2O and streaming LLM also retain a fixed window size for the KV cache, but they mitigate the precision loss due to context information discarding by employing a KV cache eviction algorithm and incorporating an attention sink, respectively. However, since these methods discard some context information, they inevitably compromise the effectiveness of large language models, LLMs, to some extent.